Our goal in section 8.2 is to integrate products. Let's talk about how we can integrate these products. We've seen products like this before. We've got x squared multiplied to x plus 1. We cannot integrate it as a product, but we can distribute and make a new integral. So this integral can actually look like x cubed plus x squared with respect to x, and then we just integrate as normal. So this one is just distribute, and then there's nothing fancy that we need. X to the fourth over 4 plus x cubed over 3 plus c, and done. What about this? This one's a product, x multiplied to the sine of x squared. What do we tend to do when we see a trig function with extra stuff in it? Use substitution. Call u the x squared. Du is 2x dx, so dx is du over 2x. Take out the dx, put du over 2x, and we get rid of our x's. Now we don't have a product anymore. We've got the integral. This 2 we can pull out, 1/2 sine of u du. And then we just proceed as normal. So u substitution sometimes takes care of our product. What about something like this? Natural log of x times 1 over x. This is a product. But when I do u substitution here, call u the natural log of x, notice all of this is its derivative, du. So this is actually the integral of u du. And then proceed as normal. Again, u substitution takes care of that scenario. Well, but what about these? Let's take a look at these products. E to the x times the product or the sum x plus 1. If I try the distributing method, like I tried in this example, what do I get? E to the x times x plus e to the x with respect to x. Did I make it not a product? I did not. I still have a product right here, e to the x times x. E to the x times x, this is still a product. I did not get rid of the product. What about this one? If I try u substitution, well, that's not more than x, that's just x. So I don't do a u substitution. I still have a product, x times the sine of x. In this one, if I were to call this the u, this is not du, so I still have a product, natural log of x times x. In all of these examples, I can't make it not a product. So what do we do? Well, before we get to the answer, let's talk about what we do when we take the derivative with respect to x of a product. Let's call the function a product of u times v. So let's say I want to do the derivative with respect to x of u times v. U and v being two separate functions. The product rule tells me take the first times the derivative of the second. So the derivative of v with respect to x plus the second times the derivative of the first, du dx, the derivative of u with respect to x. So there's my product rule when I'm taking derivatives. Now let's talk about what we do when we integrate that. So I'm going to say, let's take the integral of both sides with respect to x. With respect to x. So what I have is the integral of the derivative with respect to x of u times v with respect to x equals, and because this is a sum, I'm going to write this integral separately. The integral of u times dv dx with respect to x plus the integral of v times du dx with respect to x. What happens when I take the integral of a derivative? Those are inverse processes. They cancel each other out. So on this side, I'm left with u times v. What about on the other side? This is the integral, but not of a derivative. But I do have dx over dx, so I can simplify a little bit. Same thing here, dx over dx. So we'll write what we have left, the integral of u times dv plus the integral of v times du. I'm going to rearrange this equation a little bit. I'm going to take this integral and I'm going to subtract it from both sides. You'll see why when I'm finished. So I have uv minus the integral of v du equals the integral of u dv. That's the only thing left on this side because I subtracted that integral from that side. So here's an integral of a product. The integral of u times dv, one function times another function, equals uv minus the integral of v du. And this is the way we deal with many products when we are integrating. This is called integration by parts. Integration by parts. Integration by parts is used for integrating products of algebraic and transcendental functions. The transcendental functions, like trig functions, log functions, exponential functions. So the integral of u dv, here's a product, u times dv, is uv minus integral of v du. I'll do a few examples with you to show you how to use it. Here are hints on what to choose for the u. This is in order to follow. Start at the top, work your way down. If you have a log function, usually that's what you want to call your u. If you don't have a log function, but you have an inverse trig function, then that's what you choose for your u, and so on and so forth. Liate. Let's try to remember it like that. L for log, I for inverse trig, A for algebraic, T for trig, and E for exponential. Liate. In that order, that's what we usually think of when we want to choose our u. Sometimes it doesn't matter, especially if you don't have a mix of these, or if you do have a mix of them. Use integration by parts to evaluate numbers 1 through 10 without a calculator. So here we have the integral of x times cosecant squared of x dx. X multiplied to cosecant squared of x. Now, first thing I think of is, can I make it not a product? Because I don't want to have to do any special rules if I don't have to. So I think first, can I make this not a product? Because if I can, then I don't have to use any special rules. Well, the answer to this one is no. We have to use the integration by parts. So let's do it. Here's how. First thing I'm going to do every time I think I need to use integration by parts is write the formula. The integral of u times dv equals u times v minus the integral of v du. Now I know you already have this written on your paper, but the more you write it, the better you'll remember it. Now we go through liate. Liate helps us figure out what to choose for the u. Do we have logs? No. Do we have inverse trig functions? No. Do we have an algebraic function? Yes, we do. So u will equal the algebraic function. Here's the algebraic function, just x. So this part right here will be u. The rest of what I have, including the dx, will be dv. Now there's a lot of ways that you might see this done, especially if you look up some other tutorials, but here's a way that I particularly like that helps. So you notice there's 4 things in our formula. There's a plain u, a plain v, a du, and a dv. So I'm going to make a box, a square, that has 4 parts. One for u, one for v, one for du, and one for dv, just in that order. The simple ones on top, u and v, the derivatives on the bottom, du, dv. Then I'm going to go to what I decided was my u. U I said is x, so I'm going to put x in the u box. dv was all of this other stuff, so I'm going to put all of that other stuff including the dx in the dv box. Then I find what's missing. I find du, I find v. Well, what does d mean? D means derivative. So to go from u to du, I take the derivative. What's the derivative of x? It's 1. To go from dv to v, I take off the derivative. So I take the antiderivative. What's the antiderivative of cosecant squared of x? Negative cotangent x. Still have to remember your derivatives and antiderivatives. Now that we have our box, we can plug stuff into the formula. Now, if you didn't write down the formula, here's a helpful way to remember what to write. Once you have your box, make a 7. Here's how a 7 looks. Across and then down diagonally. There's a 7 across and then diagonally. Well, what does that mean that I write? Watch. This is what I have, integral of u dv. I want u times v. So u times v is across the top of the 7. U times v, negative cotangent x, minus the integral diagonally for my 7, negative cotangent x times du. Uh-oh, I just realized my du is not complete. It's supposed to be 1 dx. We should have dx in both of these boxes at the bottom because these are derivatives. Excuse me. So du is 1 dx. See? du. Now, I still have an integral, but at least this integral is not a product anymore. So now I can take that integral. Let's simplify a little bit first. This I can write as negative x cotangent x minus, that's a negative, so I'm going to change this to plus the integral of cotangent x dx. The 1 just multiplies in, and that's fine. Now, I think of the integral of cotangent x is natural log of the absolute value of sine of x, and when I'm all done integrating, plus c. Don't forget the part we had at the beginning, negative x cotangent x, and there we have our integral. Why, thank you. That is a pretty cool process. Now we can take integrals of most products. Go ahead and try number 2 on your own, pause the video, and check your answer at the end of your notes. All the answers are typed there. Now, if you're watching this without a note sheet, your answer for number 2 could be the following. If you'd like to see me do this example, check out the next tutorial. Let's look at what I mean by integrating when it looks like we have a single term. Integral of natural log of 3x dx. Now, we haven't talked about integrating natural log functions, like as in there's a rule to memorize. There is, but we haven't memorized it because we don't really need to. So here's what we do when we think we just have one term or one factor or one expression or one function, and it doesn't look like we have a product. That's the thing here. It doesn't look like we have a product. Well, we do have a product. Now, if we write down our liate, logs is what we have. We have logs. So log is our u. Well, all of this function is the log function. That's our u, which means the rest of it, or just the dx, will be our dv. Now again, the more you write this formula, the more you'll remember it. The integral of u dv equals uv minus the integral of v du. Let's make our box. Put our 4 quadrants in it. At the top, the simple ones, u and v. At the bottom, the derivatives, du and dv. And we'll fill in with what we have. We said u is the natural log function, natural log of 3x, and dv is just dx. And then we do the others that we don't have. Take the derivative of natural log of 3x. That's going to be u prime, which is 3, over u, which is 3x. Well, that simplifies better. 1 over x, don't forget dx, 1 over x dx. Take the antiderivative of just dx, which kind of is just 1 dx, and that's x. And now we can fill in our formula or draw the 7, uv, and then v du. If we follow the 7, uv looks like this. Natural log of 3x times v, x, minus integral v du. X du is 1 over x dx. Now, we can simplify a little bit. Here, if we put this x in the front, then we don't need to use parentheses. And here, x cancels out with 1 over x, and we're left with the integral of 1 dx. This is easy to integrate, no more product. This is just x, and don't forget plus c at the end. Now we have our integral. Try the next one on your own. Maybe pause the video. Check your answer in the back. Now, there may come a time where you have to do the process more than once. Let's see when that happens. So again, integral u dv minus, equals uv minus integral v du. And we write liate. I have a log function here, and logs come first, so log will be my u. This whole function can't do anything to not make it a product, will be my u. Whatever else is left will be my dv. And then I'll make my box with my 4 quadrants, u and v at the top, du and dv at the bottom. U is the natural log of x, function squared, dv is dx. Take the derivative of this. Be careful taking the derivative of this because you have to use a bit of the chain rule. 2 goes in front times the inside to the first, and then the derivative of the inside, which is 1 over x dx. Take the antiderivative of this side, x. And now we do our 7. uv and then v du. Let's write it down. U times v is natural log of x squared. V is x minus integral v du. X times all this guy. 2 natural log of x times 1 over x dx. Now, I can simplify a little bit, like x over x does cancel out, and I can move this around so I have x times the natural log of x function squared minus the integral of 2 natural log of x dx. Now again, like in the previous example, I don't know the antiderivative of natural log of x. So I do this like I have a product. And I use this process more than once. Here's the second time. Here is my u. If I want to, I can take the 2 with it, or I can send it with the dx. It doesn't matter where it goes. Now, since it's with the right next to the natural log, it might be easier just to say all of this is my u, and then this part is my dv, and let's make another box. Now be careful, because we're calling things u and v again, but they're different things. u, v, du, dv. U is our 2 natural log of x. dv is dx. Do the derivative, 2 times 1 over x, or 2 over x dx. Do the antiderivative, x. Now, for this part only, we're doing the integration by parts rule again. So for that part only, we've got are 7. Boom, boom. For that part only, 2 natural log of x times x minus integral x times 2 over x dx. Remember though, all of that was subtracted from the first part of our integral we did before. Now let's simplify a little bit working in the inside here. This goes away, so we're left with the integral of 2 dx. That is just 2x. We have minus and all this part, 2x natural log of x, bracket, minus, and everything we had before, x natural log of x, function squared. Don't forget plus c, and either stop here or distribute your negative. For example, it could look like this. If we have any like terms, combine them, and we're good. I agree. Try number 6 on your own. Check the answer in the back or right here.